Okay, here we go. Now we're getting into the fun part of chapter 9, and that is trigonometry. So you're going to get a little taste of what trigonometry is all about. We're going to use it in really cool ways, but it fits perfectly into this chapter because trig is something that you have to have a right triangle in order to use. And so it fits right in with what we're doing. It kind of fits in with all of these shortcut ideas that we have been doing the last few days. And so we're going to kind of get you introduced today. We're just going to give you the very, very basics today. And then tomorrow and the next day, we're going to kind of build on that and show you how to use it a little bit more. So today is the essentials. So if you have questions, make sure you're asking those questions in class if you're confused on something. So we're going to start off with a little activity here to show you where trig ratios first came from, okay? So notice I have 3 triangles up here, and I want you to ignore the bottom, but you have an idea of where we're heading, but I want you to just focus on the 3 triangles at the top of your table. So maybe you want to pause and get your table all set up. But notice these 3 triangles. I have a 30 degrees and a 90 degrees in each. If I have a 30 degrees and a 90 degrees, that remaining angle must be 60 degrees in every single one, right? So I have a bunch of 30, 60, 90 triangles. So what I want you to do, notice in each triangle, I have one side given to you. I want you to bring those 30, 60, 90 shortcuts back. And I would like you to find the missing sides for each of those 3 triangles. Ignore the bottom for right now. So pause your videos, get your table set up, and fill in the missing sides on each one of these, okay? So here we go. The first one, the side across from the 30 is 1. So if I'm doing my shortcuts, so for all of these, I would have x across from the 30, x radical 3 across from the 60, and 2x across from the 90, right? I'm going to put all of my shortcuts in all 3 just so that I have them. Across from the 30 is x, across from the 60 is x radical 3, across from the 90 is 2x. All right, so in my first triangle here, x equals 1, so 2x is 2, and x radical 3 is, 1 radical 3, or just radical 3, right? In my middle triangle here, let's see, x radical 3, I should probably have highlighted to show you where those came from, right? X equals 1 on that one. So in this one, I have x radical 3 equals 2 radical 3, which means x will be 2. And 2x is 4. All right, and then in my last one, I see that I have 2x equals 6, which means that x is 3. And then x radical 3 would be 3 radical 3. And I'm just realizing that I wanted to use different colors for these. So let's see here. I just want to switch it just for future. And these 2 give me this color. Okay. Now, down below, I have some ratios of sides set up. So that's where trig is all about. It's actually, they're called trig ratios. So it comes from ratios of sides. So what I want for the first one here, I have the ratio of A over C. And I have it for all 3 triangles. So let's try and find the ratio of A over C. So in my first triangle, A was 1, right? A was 1 and C was 2. So my ratio is 1 over 2, or 1/2. Okay. In my middle triangle, A is 2, C is 4. So my ratio would be 2 over 4. Ooh, but I can reduce that. Oh, and it reduces to 1/2. In my third one here, A was 3 and C was 6. So my ratio is 3 over 6, which I can reduce to 1/2. Huh. So in a 30, 60, 90 triangle, the ratio of A over C, right, is 1/2. Huh. Okay. Now let's find the ratio of B over C. So in my first triangle over here, B was radical 3 and C was 2. So my ratio would be radical 3 over 2, and nothing I can reduce. In my middle triangle, B was 2 radical 3 and C was 4. So I have 2 radical 3 over 4, but I can reduce the 2 over 4 to become radical 3 over 2. Okay. Oops. Now, in my last triangle, B was 3 radical 3, and C was 6, so I have 3 radical 3 over 6. But the 3 and the 6 can reduce, so I get radical 3 over 2 again. So the ratio of B over C in all 3 of my 30, 60, 90 triangles reduced to radical 3 over 2. All right, let's check out this last ratio, A over B. So A is 1, B is radical 3. Now be careful on this one. Run over radical 3. I can't leave a radical in the bottom, so I have to clear it off the bottom. So it gets radical 3 over 3. All right, in my middle one, A is 2, B is 2 radical 3. So I have 2 over 2 radical 3. Ooh, the 2's are going to cancel, right? And I have to multiply by radical 3, so I get radical 3 over 3 again. It's the same thing. And finally, 3 over 3 radical 3. I'm hoping you're figuring out what's going to happen. 3 over 3 radical 3. 3's cancel, but I have to clear the radical, and I get radical 3 over 3 again. So this is what a bunch of mathematicians noticed a long time ago when they were first kind of using Pythagorean theorem like crazy. And they noticed that I end up, if I have the same angle measures, when I find these ratios of sides, the ratios of sides are always the same. And that's what they got really excited. Now, I showed you with just 30, 60, 90 triangles because you know those shortcuts and it was really quick to do. But they noticed this with every single different angle measure. They checked 28-degree angles. They checked 29-degree angles. They checked 30-degree angles. They checked all of the different types and found that those ratios were the same. And they said, wow, we can use that, right? So if I look back at what we were having here, when I said A over C, well, C was the hypotenuse, right? C is always the hypotenuse. And when I said A, that was the side that was across from the 30 degrees, right? This was the side opposite the 30 degrees for every single one. So this ratio A over C was really opposite over hypotenuse. Hypotenuse. So the side opposite over hypotenuse for any triangle, right, for depending on which angle you are looking from, but this ratio of opposite over hypotenuse was the ratio that we called sine. Now, sine we abbreviate with S-I-N, but do not call it sin. That is a swear word. Yuck, gross, don't do it. It is the ratio called sine. It is abbreviated S-I-N, but the name of it is sine, and sine is opposite over hypotenuse. Now, when I looked at that middle ratio, when I did B over C, again, C was the hypotenuse, right, down here. Why is my pen not writing? Sorry. Hypotenuse. But B this time, from the perspective of this 30-degree angle, B was the side next to it, or the adjacent side. So B over C was adjacent over hypotenuse. And when I have that ratio of adjacent over hypotenuse, that I call cosine. Again, that ratio is called cosine. It is abbreviated COS, but do not say cos or cos. That's ridiculous. That's a swear word. Yuck. It is called cosine, abbreviated COS, but you say cosine. So cosine is adjacent over hypotenuse. Then my last ratio was A over B, right? So I don't have the hypotenuse involved at all. From this perspective of this 30-degree angle, A was the opposite side, and B was the adjacent side. So that ratio, opposite over adjacent, that is what we call tangent. All right, tangent is abbreviated TAN, but again, don't say tan in a math classroom. That's swear words. We're not talking about going to the beach, right? It is called tangent. So make sure that you call it tangent. It's just abbreviated as TAN, and that is opposite over adjacent. Those are our three main trig ratios. And again, a ratio of sides. That's all a trig ratio is, a ratio of sides. So I have sine, cosine, and tangent. And it depends on from whatever angle you're looking from, right? Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Okay, so there is a way to remember those, and that is called SOH CAH TOA. SOH CAH TOA is how we remember our trig ratios. So, SOH. And it not only does it tell you what those letters stand for, but the order that they come in. So S stands for sine. Sine is opposite over hypotenuse. SOH. Opposite on top, hypotenuse on the bottom. CAH, CAH, cosine, is adjacent over hypotenuse. And the last one, TOA, tangent, is opposite over adjacent. So make sure you write SOH CAH TOA down. Put it nice and big in your notes. Put a big box and a star around it, right? If you want to write, if you want to write it like this with our abbreviation and you want to put opposite over hypotenuse underneath it, cosine is adjacent over hypotenuse, tangent with our abbreviation is opposite over adjacent. However you want to put it in your notes so that you will see it quickly. SOH CAH TOA is the way to remember it. The big deal is you have to have a right triangle in order to use these. If you don't have a right triangle, then you can't use a trig ratio because there is no such thing as a hypotenuse in any other type of triangle. And even with tangent, it's not using the hypotenuse, but you got to know which side is the hypotenuse in order to know which one's the opposite and the adjacent. So you have to have a right triangle. So again, it is essential that you mark your right angles in these triangles as well. So let's see how to find those ratios in a triangle now. That's not one of our shortcuts. So let's see. Here's my triangle ABC. Just focus on the one on the left right now. Triangle ABC. 7, 24. I'm gonna need all three side lengths in order to make my ratios, right? Can I fill in that missing side length? 7, 24. That's a Pythagorean triple. So still watch out for those. 7, 24, 25, because the missing side is across from the right angle, right? So this one is 25. Okay, now if I'm going to use my trig ratios, I kind of got to know, right, that side AC, this is the hypotenuse for sure, right? Okay. Now, knowing which side is opposite and which side is adjacent depends on which angle you're talking about. So in my last ones, I always did from the 30-degree angle, but you could have done it from the 60 as well. So that's why whenever we use one of these trig ratios, we always note which angle we're looking from. So for example, letter A says the cosine of angle A. Cosine. Cosine is of angle A. So here's the direction. This is the angle I'm looking from. Cosine is adjacent over hypotenuse. So what we know which side is the hypotenuse, right? So hypotenuse is 25. So adjacent means the side next to angle A. Which side is next to angle A? That's the 24, right? So this is the adjacent to angle A. So my ratio would be adjacent 24 over hypotenuse, which is 25. That's it. 24 over 25. That's the ratio cosine of angle A. Done. No more to do. All right, now the next one says tangent of angle C. So this time I'm looking from the perspective of angle C, right? Tangent, TOA. Tangent is opposite over adjacent. Okay. Now, opposite, side opposite would be the 24 this time, right? 24 is opposite of angle C, so it's adjacent of angle A, but opposite of angle C. So 24 is on top of our fraction this time. And the adjacent, you're like, wait, there's two sides that are next to angle C. Yes, but one of them is the hypotenuse, and that has to take precedence. So next to angle C would be the 7. So adjacent would be 7. So my ratio is opposite over adjacent, so it would be 24 over 7. That's the ratio. That's it. That's all we got to do. All right, last one here says we're going back to angle A. So sine of angle A, so again, from the perspective of angle A, sine is opposite over hypotenuse. Opposite of angle A is the 7. So 7 over, and the hypotenuse we know is 25. 7 over 25. So that's all we're doing here is just making those ratios. Now, on this one, none of those fractions could be reduced, so those are just our answers. You always reduce fractions, though, even with trig ratios. So if you get a fraction that can be reduced, definitely reduce it. None of ours just could on this one, so that's why we're leaving them how they are. All right, last triangle over here. Triangle ABC, two sides of 13, bottom is 10, and we're trying to find the sine of angle C. The sine of angle C. Okay, now be careful, right? Sine is opposite over hypotenuse. Hang on. Where's the hypotenuse? You have to make sure that you have a right triangle in order to do a trig ratio, right? So you might be saying, hey, well, if there is no right angle, then there's nothing I can do. It's a no solution. That's not true. You guys can do a lot, and you just might have to manipulate your picture just a little bit. If I need to have a right angle in my picture, what could I draw in that would form a right angle? I could draw in an altitude, right? I could draw in that altitude that's missing, but I know every triangle has an altitude. In fact, they have 3, right? So I could draw the one that I want in order to make a right angle. Now, did you notice that I had an isosceles triangle here? When I have an isosceles triangle, 13 and 13, my altitude is also my median, right? Because really that altitude is forming two congruent triangles. I could prove them congruent using HL, reflexive property, on the one I drew in, right? And I have my hypotenuse is congruent. So that means I know that it split that bottom side exactly in half. So I have 5 and 5. And I'm trying to, oh, hang on, the altitude here, I have 5 something and 13. 13 is the hypotenuse. That's a Pythagorean triple. Pythagorean triple, 5, 12, 13. So that altitude's height was 12. Now that I have all of this filled in, I have my right triangle. Now I can use my trig ratio, but make sure that you're using the trig ratio on only the right triangle. So it has to be that little half of the triangle that we created when we drew in our altitude, not the whole original one. You can only do a trig ratio on a right triangle. So going back to what my trig ratio was, it is opposite over hypotenuse. So in this little right triangle, the side across from the right angle is the hypotenuse, so 13 would be the hypotenuse. And I want opposite of angle C, so 12 is opposite of angle C. So my ratio is 12 over 13. So just make sure you have to have a right triangle in order to do a trig ratio. If you don't have a right triangle, see if you can draw in something that would create that right angle. Don't give up and call it a no solution until you've exhausted all of your possibilities.